So let's look at exercise 4. And this is about going from Bohr to Balmer. As I'm often fond of saying, imagine that you're Bohr and you're doing your Nobel Prize winning calculation of the energy levels of the hydrogen. Crazy and self-contradictory calculation. That's exercise 3, by the way, which we won't go through today. Bohr's calculation of the energy levels of the hydrogen atom is a crazy contradictory calculation because it mixes, and this is ultimately contradictory because it mixes classical concepts such as a billiard ball electron orbiting the nucleus of a hydrogen atom. It mixes classical concepts with quantum concepts such as the demand that the angular momentum be quantized. So you've just done this mad calculation and you're not sure whether to publish it or not. You're not sure if you're going to get thrown out of the academy or viewed as a nutcase for publishing this crazy theory, this Bohr theory of the hydrogen atom. And pioneering work, by the way, is necessarily controversial. But you know that there was a teacher who in 1885 came up with a formula for the then known spectral lines of hydrogen. So you take glowing hydrogen gas, you pass it through a prism. When you pass it through a prism, you get a series of spectral lines. And at the time, there were 8 known spectral lines. And let's label the wavelength of those spectral lines, as Balmer did, by an integer p, where p is 1, 2, 3, 4, 5, 6, 7, or 8. And what Balmer noticed, purely empirically, there's no theory here, he just noticed empirically that if you have some constant c, then the 8 known spectral lines of the time obeyed this equation. Again, p being an integer, this is equation 8 of the notes. But you're Bohr, and you've just worked out a formula for the energy levels of the hydrogen atom. If your formula is to be taken seriously, then the Bohr formula must produce this result as a special case, and that's what the exercise is. Can you show that the Bohr result reduces to the Balmer result? The Bohr result for the energy levels of the hydrogen atom, can you show that it reduces to, or as a special case, Balmer's formula? And that's the key question. If, by the way, Bohr did this and it didn't give the previously known result, then Bohr would have known that his theory was wrong. But as a consistency check, the higher theory or the more general theory or the theory that claims to be more general should reduce to the less general theory in the domain of validity of the latter. So let's do this now. Excellent. All right, so let's just revise Bohr's theory. Bohr had a theory for the energy levels of the hydrogen atom. And we have a series of energy levels. And those energy levels obey the Bohr formula, which is as follows. The energy of the nth state, the nth excited state, n being an integer, going from from 1 to infinity, all the way up to infinity. And these are the energy levels, or the nth energy level of the hydrogen atom. According to Bohr, it's negative, some constant. That constant is positive on n squared. Now, the particular form of the constant, which I've called squiggle, is immaterial for this particular problem, but let's write it out. It's a positive constant, the mass of the electron, the 4th power of the charge on the electron, some constant, 32 pi squared, permittivity of free space squared, and also the reduced Planck's constant squared. But I've just stuffed that all into some positive constant psi. All these energy levels are negative, right? If n becomes arbitrarily large, if n becomes infinite, then E is going to tend towards 0. Yep. So the highest energy level is in fact 0, and all the energy levels for n not infinite are negative. So as a question for you, what does it mean for the energy levels? And these are electrons, or the single electron orbiting a nucleus n in the Bohr model of the hydrogen atom. The energies of all these electrons are negative, What does that mean? What does this negative sign mean? It means the system's bound. Beautiful, a beautiful succinct answer. This negative means that the system is bound. In other words, the electron can't escape to infinity. If that electron had a positive energy, if it had a positive energy, then it could escape to infinity, right? The energy of the electron, if it's positive, the electron could escape to infinity. The fact that the energy of the electron is negative means that it's bound. We have an atom, we have an electron stuck to the nucleus. So you got this formula and you want to get the Balmer formula as a special case. So let's draw this energy diagram again. And there's a whole lot of energy levels labelled by N. But I want to pick out two of them. I'm going to pick out an energy level called A and an energy level called B. And I'm going to imagine the atom de-exciting. So here's an excited state of the hydrogen atom. Here's a de-excited state of the hydrogen atom. Lower energy down the bottom, higher energy up the top. N equals A or N equals B. And when the atom de-excites from the higher energy state to the lower energy state, it's going to emit a photon. The de-exciting atom is going to emit a photon. And we can ask the question, what is the energy of the photon released when the atom de-excites from state A to state B? And it's just going to be, it's going to be the initial energy minus the final energy, because the initial energy of the electron minus the final energy of the electron is the energy given to the emitted photon. Yep. What is EA? It's minus squiggle on A squared. What is EB? It's minus squiggle on B squared. So let's make our lives easier and factor out a squiggle. Again, this is squiggle, but I want to save chalk. We've got 1 on B squared minus 1 on A squared. Now we want to work towards the Balmer formula here. Again, I want you to be Sherlock Holmes-like in your logic. And so let me ask you a vague question. This is where I'm at. And we know what formula we want. We want equation 8 at the bottom right of the top panel. What do I need to do to this formula to get myself... I don't know how to derive equation 8 yet, and you're Bohr, you're doing this for the first time. What do I need in this formula that I don't have? Yep. Lambda, beautiful. I asked the question, what do we need that we don't have? It's lambda. Now this is the kind of logic, when you're solving problems that haven't been solved before, sure this has been solved before, but when you're doing problem solving in whatever jobs you do post your degree, you'll be working on unsolved problems. That's the logic you need to give. You need to look back at the problem and see the simplicity. You want a formula for lambda, there's no lambda here, therefore you need to stick a lambda in there, right? Beautiful logic. How do I inject a lambda into this formula? Yep.
E equals HC on lambda.
Beautiful. E equals HC on lambda. I mean, everything on the right-hand side, these are just integers and constants. The only place we can convert into a wavelength is energy. Yeah? The bigger the energy of the photon, the smaller its wavelength. So the formula E equals HC on lambda, which is equation 4 of the course, relates the energy of a photon to its wavelength. By the way, again, this is not just a bunch of Greek and Roman symbols. It has physical meaning. As the wavelength gets smaller, the energy gets bigger. The energy of an X-ray photon is higher than the energy of an infrared photon because the wavelength is smaller for the X-ray photon. So this is E equals HC on lambda, which we now use. So let's take our boxed equation, and instead of E, we'll write HC on lambda. And just to keep the notation a bit more informative, this is the wavelength of the photon associated with the electron in the Bohr atom de-exciting from a high energy state A to a lower energy state B. That's hc on lambda. We've got squiggle, 1 on b squared minus 1 on a squared. And currently a and b are arbitrary integers. Now the formula we want says lambda equals something. This is again equation 8 in the top right panel. So let's solve this for lambda. I'm going to take the reciprocal of both sides and then multiply through by hc, just to solve for the wavelength. So I've taken the reciprocal of both sides and multiplied through by hc. I take the reciprocal of both sides and multiply through by hc. Now I need to take the reciprocal of this, so let me just combine the fractions. I'll get a squared minus b squared over a squared b squared, which I then reciprocate. A squared minus b squared over a squared b squared. All right. So we've now got Bohr's prediction for the wavelength of this photon. And now we stare at this, and we stare at equation 8. And what, again, these are deliberately vague questions, because when you're solving problems that have never been solved before, you don't know what the hell you're doing because no one's done it before, right? So I'm going to ask a deliberately vague question because that is the context you'll be in when solving new problems that no one's ever solved. What does this equation say to you to do next? Sorry? P squared. B squared is 4, beautiful. Lambda equals something is equation 8. You focus on the denominator. There's a p squared minus 4. So this is telling you that b squared has to be 4, hence b equals 2. So we can let b equals 2. So the wavelength. Let's leave A alone for now. We're de-exciting to the second excited state. And this now has physical meaning. This is our energy diagram. This is our ground state, n equals 1. This is our second excited state, n equals 2. And we're going to be decaying from some high energy state down to the second excited state. So this is often called the first excited state. This is called the ground state. So we've done this, and we've learned something physical. We're decaying to the first excited state, n equals 2. What else does this formula say to you? Besides b squared, besides b equals 2? I want this denominator to look like p squared minus 4, hence? Beautiful. So A should be p. Now, I just made a random guess of what I call the initial and final state. I tried to be clever, trust me, and guess which one was initially p. Couldn't do it, so I just called them A and B, but this is telling me that I need A to be p. So I'm decaying from the pth excited state to the second excited state. So let me just rewrite this formula with A equals P and B equals 4. And I'm going to have an I, by the way, on the Balmer formula. Some constant times P squared. So we've got H, we've got C, we've got squiggle. A squared is now P squared. Again, look at equation 8. B squared is now 4. And the denominator is p squared by minus 4. So this thing that I'm circling, we need to be careful. This little c is the speed of light, and this capital C is the c appearing in Balmer's formula, equation 8. We now have the Balmer formula. Why? Physically, this is decaying from the pth state to the second state, or to the first excited state. What happened to n equals 1? If you go back to 1885, what about all the decays down to the ground state? Surely an excited hydrogen atom can decay down to the ground state.
Maybe they are not visible?
Maybe they're not physical?
Visible.
Visible. Yeah, maybe they're not visible. That's the key. Absolutely, a hydrogen atom can decay down to the ground state. It'll lose more energy in the process, giving a higher energy photon. And if that energy is too high in energy, for example, in the ultraviolet, then it's not visible. So the spectral lines of hydrogen in 1885 were just the visible light ones. This gap is too large in order to give visible light photons. We have the more general formula given by this expression here, but the formula for Balmer is this. And again, if you're Bohr, you're very excited at this stage because people knew what this constant C was empirically, capital C. People knew what H bar was, people knew what C was, people knew what squiggle was. These things had to be the same. So you're actually predicting the Balmer formula as a consequence of the Bohr theory, and everything works out fine, that these things are in fact equal, and this was considered by Bohr as a triumph of his then new theory. Exercise 7. I made a lot of dogmatic claims regarding the bricks, not of the bricks of this building, but regarding the bricks out of which we build arbitrary wave functions. I made several dogmatic claims regarding the plane waves. These objects out of the superposition of which we construct arbitrary wave functions. In particular, I'm thinking of the Fourier integral in equation 25, which is a weighted superposition of plane waves, giving an arbitrary wave function. So just to remind you, our plane wave has wave fronts. Now this thing I'm underlining is the phase of the wave function, of the plane wave function. It's a function of position and time. These wave fronts are surfaces of constant phase. I claimed several things, for example, that the wave vector k, which will have Cartesian components kx, ky and kz. I claimed that the wave fronts are planar. I claimed that the wave fronts were separated by a distance of lambda. More precisely, if you have two consecutive wave fronts with a phase of w and w plus 2 pi, I claimed that the distance between those wave fronts, those surfaces of constant phase, was lambda. Lambda is also related to the magnitude of the wave vector, which I call the scalar k, as follows. I also claim that these wave fronts move in the direction of the wave vector k. And as always, I said you should take nothing on faith. You shouldn't believe me. You need to do exercise 7 to prove those various statements. So this is exercise 7. Now the first thing we need to prove is that the surfaces of constant phase, these wave fronts, so we need to prove three things. The first of which is that these wave fronts are perpendicular to the wave vector k. Now I'm about to do something very profound. Let this be an XYZ coordinate system. In fact, I've got a watch and I've got an XYZ coordinate system. And I could choose to describe the physics of the world with that XYZ coordinate system and this t. Now this is a profound thing. I've just shifted my fingers and nothing happened. That's very profound, right? Watch again. I've just done an experiment. I've changed my coordinate system and the world doesn't give a stuff. As I often say, the world doesn't care where you stick your fingers. In other words, the world doesn't care which coordinate system you choose. Why not choose your coordinate system to make your life as simple as possible? So we have a plane wave, and it's described by some wave vector k. Let it be this stick, tail and tip. And this is my coordinate system x, y, z. And let my index finger be the z coordinate. Now I'll put this wave vector in an arbitrary direction, but I can choose my coordinate system wherever I want. Let me be aesthetically pleasing / lazy and make my z coordinate point in the direction of the vector. Now the vector's in an arbitrary position, but without loss of generality I can align my z-axis with the vector and nothing's changed. So let's do this. Now I didn't do this in the solutions, but that's cool. You shouldn't just answer questions the way that I answer them. I don't answer my own questions the way that I answer them. I always look for simplifications, always look for more elegant, more transparent, more direct routes to solve any difficult problem. Let's make our life easy, and with this arbitrary wave vector k, let's align our z coordinate with that wave vector, and then we just have a right-handed coordinate system, x, y, z. if that's not right-handed, just switch x and y around. I can never get it right. So we've aligned our z coordinate with the wave vector. And so in this coordinate system, the wave vector, and there's no loss of generality, has one component. And I'll call it k, because I know that the magnitude of the wave vector is the scalar k. So this is now our wave vector k, no loss of generality. R is still x, y, z, but the k dot r that appears in our plane wave is now going to be 0 times x plus 0 times y plus k times z. So in this coordinate system, the phase of the wave function is kz minus omega t, and our plane wave is a z-directed plane wave. And so let's now prove the various things we want to prove. So the first is that the wave fronts, well, the wave fronts are surfaces of constant phase. There'll be a surface where the phase phi is a constant, fair enough. Kz minus omega t is a constant. So kz equals omega t plus a constant. Let's freeze time at some particular time, t naught. So at some instant of time, let's divide through by k. The constant divided by k is another constant. Okay, let me call it a constant with a capital C, right? So the surface of constant phase, in other words, the wave front, at a given instant of time, for this arbitrary wave function, but I've chosen my coordinate system cunningly, the wave front is z at a particular time t naught. Omega is fixed, k is fixed, t naught is fixed, the constant is fixed, hence z naught is a constant, or hence z is a constant. And this defines a plane. Remember, we're in 3D. The plane z equals constant. You give me any x value, any y value, and a particular z value. Z equals a constant, z equals this constant. That defines a plane. This proves that the wave fronts are a plane perpendicular to the z-axis. But the z-axis is the same as the, is parallel to the wave vector k. So we've just proven that the wave fronts are perpendicular to the wave vector. And sure, you can do all sorts of fancy linear algebra if you don't make the change of coordinates that I just did, but why not make your life simpler? The second of three things we want to prove is the following. Suppose we take two wavefronts. So here's two wavefronts, which we now know to be parallel, planes parallel to the z-axis, and therefore two wavefronts will be parallel to one another. And the first of these wavefronts is going to have a phase which is some number we'll call w, not omega but w. And the second wavefront is going to have a phase which is 2 pi larger than this. Again, my claim was that when we had a series of wavefronts spaced by lambda, the phase would increase in jumps of 2 pi between consecutive wavefronts, and you're moving in the direction that the k vector is pointing. So the question is to prove that the spacing between these wavefronts is indeed lambda, the de Broglie wavelength or the de Broglie wavelength as claimed. All right, let's go back to the phase equals kz minus omega t. And this is an omega. For our first wavefront, phi equals w, and that will correspond to a particular z that I'll call z1. Second wavefront, w plus 2 pi, a different z, which I'll call z2, minus omega t. Now we can freeze time at any time. I could call that time t naught, I could just call that time t. So let's consider a particular time t, and these are two particular wave fronts. We want to know the separation between them. Well, the separation between them is going to be z2, because this coordinate here is going to be z2 minus z1. So let's take the second equation and subtract the first. W minus w disappears. We're left with 2 pi on the left-hand side. kz2 minus kz1 minus omega t minus omega t. Now k is the same thing as 2 pi on lambda. I can cancel the 2 pi's, bring the lambda through, and we get that lambda equals z2 minus z1, which makes us happy, because that's what we want to prove. The distance between these two planes is z2 minus z1. We've just proven this is lambda. Again, the solution in the notes, as I was reading it on the train this morning, I thought, nah, you can do this much more easily than this. Always look at anything I say and ask, how can you simplify it? Or just how can you do it differently? The way I do something and the way you do something should be different, or can be different. You can do it the way that works for you best. You can do it a better way than I did. I always encourage that, by the way, as well as finding mistakes in anything I do. The third one is to prove that the wavefronts propagate in the z direction. Now I'm having a bit of a mental blank here, so we want to prove that the wavefronts propagate with time. As time increases, as this thing grows older, we want to prove that the wavefronts propagate parallel to, in other words, in the same direction as the wave vector k. But again, I'm having this mental blank, so can someone help me? The simplest possible solution you can think of to demonstrate that the wavefronts propagate in the k direction. Yep.
Show that if the phase stays the same and time increases, the x of z increases.
Beautiful. Show that if the phase stays the same and time increases, then z increases. So let me repeat. Show that if the phase stays the same and time increases, that z increases. So let's take, which expression? The very bottom of the top board, right? Z, this is the z coordinate of a wavefront. Angular frequency is fixed because the energy is fixed. We've got t naught that I'll now write as t, because t is now going to be considered a variable because we want this wavefront to grow older. This constant is just the particular phase of the wavefront. The wavefront is the surface of constant phase. If we keep this fixed, as was stated correctly, then this constant is the same. But if we now consider t to be a variable, then what is the wavefront? Well, z is proportional to t. dz dt will be the speed at which the wavefront moves, and that's going to be omega on k. And that's a positive number if omega is non-zero. So this is just the wavefront moving in the z direction. Yep. At t equals naught. This is a z coordinate at t equals naught. The wavefront will be z equals a constant, whatever that might be. But you wait a little while, you let t be 1, for example, and the wavefront will have moved to the right. It'll be that same constant plus a little bit, omega on k. So the wavefront is moving with time. And because this is an arbitrary wavefront, every one of these infinity of parallel planes moves at the same speed in the z direction, which is parallel to the wave vector k. Again, the most important lesson here is to stare at a problem and ask yourself, how can I do it as simply as possible? Before I go on, questions, comments or queries about anything that we've done so far? I'll tell you a secret. Everything I do in this course is wrong. Now what I mean by that is the following, that if you take a sufficiently rigorous perspective, then almost everything that I do in this course is wrong in the sense of not being rigorous at the level that will be satisfactory for a pure mathematician. So if you stare hard enough at anything that I do, then if you ask the question, is this sufficiently rigorous, and you keep trying to make the argument more rigorous, you will ultimately be able to drive a bulldozer through every piece of logic that I give. the point is that, and everyone has a different level of rigour. As a physicist / applied mathematician, I have a particular level of rigour, which is lower than that of a pure mathematician. So the point is, for those of you who for example, are majoring in pure mathematics, or who have a major in pure mathematics or have a deep interest in it, I do, by the way, myself, but the point is, you can always ask the question, how could various arguments be made more rigorous? If you want to see quantum mechanics made more rigorous, then look up any textbook which has a title such as Axiomatic Quantum Mechanics, of which there are several available. I now want to move on to exercise 11, which is about the Schrodinger correspondence rules. There's also an opportunity to revise some of the vector analysis that's used in this course. Again, I want to make the point that complex numbers, we use them every day in this course. Linear algebra, we use it regularly. You saw an example here. Although I was trying to avoid linear algebra as much as possible. We use differential equations every day. And as a case in point, this will help revise some vector analysis. Yep. So let's do it. Here is the wave function for a plane wave. It's a function of position and time, but I won't write that explicitly. In equation 28, we learned that if you take a plane wave and hit it with the operator IH cross d by dt, what you get is the energy of the plane wave times the plane wave back again. Again, you'll recognise this as an eigenvalue equation. Operator acts on eigenfunction to give the eigenvalue times the eigenfunction, so the plane wave is an eigenfunction of the energy operator, with the eigenvalue being the energy itself. This is a temporal derivative, a spatial derivative, in this case the gradient operator from second year vector analysis. If you apply it to the plane wave, you get a corresponding eigenvalue, which is the momentum of the plane wave. Now the eigenvalue happens to be a vector. What the hell does it mean to have an eigenvalue that's a vector? Again, I'm a bit stuck. I thought eigenvalues were scalars. Operator acts on eigenfunction to give a number times the eigenfunction. How can an eigenvalue be a vector?
Well, momentum has direction.
Momentum has direction. Momentum has three components. This is not one equation, this is three. This is three scalar equations. As it was pointed out, momentum has direction. This is three equations, the first of which is minus IH cross d by dx of psi plane wave equals the x component of p times the plane wave. And there our eigenvalue is a scalar. We have a similar equation for y and a similar one for z, but you put them together in one vector equation. So this is really three eigenvalue equations, and the key point is, as you stated, that this is a vector, it has direction, it has three components. Hence, equation 29 is three eigenvalue equations. But we need to derive these things now. So let's look at the first one. And sorry, by the way, just to remind you that these were used to motivate the Schrodinger correspondence rules, that E be replaced with an operator. This is the first of two Schrodinger correspondence rules, and also that P in classical mechanics, E in classical mechanics becomes an operator in quantum, P in classical mechanics becomes an operator in quantum. So these Schrodinger correspondence rules were used to motivate, to derive in inverted commas, the Schrodinger equation. But I want to prove equations 28 and 29. So let's begin with equation 28. So we've got IH cross d by dt. This is acting on the plane wave. And the plane wave was at the very top of the board, e to the I k dot r minus omega t. What do I do next? Derive it, yeah, good point. Derive it, how do I derive it? Sorry? Chain rule, yep, beautiful. Now, because this is a partial differentiation with respect to time, the suggestion was to use the chain rule, but suppose I'm being a bit slow. Before I use the chain rule, I say, okay, this is a partial derivative with respect to time. As far as that partial derivative is concerned, t is the only variable. Now this can be written as a product of two factors, which is e to the I k dot r and e to the minus omega t. And as far as d by dt is concerned, this factor here is constant, at least with respect to t. So my time derivative just acts on e to the minus I omega t. And now we use the chain rule to differentiate this. So with the chain rule used to differentiate this object, when we differentiate with respect to time, what you pull out is a factor of minus I h cross. So minus I h cross, yep, minus I h cross. No, it isn't. Sorry. We pull out a factor of minus I omega. So minus I and then omega. And then you're left with e to the minus omega t again, which I might as well just shove back in the plane wave. So when we apply this operator to the plane wave, we get this factor times the plane wave. The minus I squared is 1, so I'll rub it off. And h bar omega is the energy. So I rub it off and replace it with the energy. And this is what we wanted to prove. So that's good. We've just proven equation 28. By the way, never in my life, I was about to say never in my life have I flicked the boards up and it's landed at exactly the top 3 times in a row, but we've just done it. Fantastic. All right. Now we want to prove equation 29. Yep. So let me just write it out again. What we'll call the momentum operator acts on the plane wave to give the momentum vector times the plane wave. Again, I'm still freaking out slightly about this idea of a vector eigenvalue, so let me write this out as 3 scalar equations. Minus I h cross d by dx acts on the plane wave. X component of this object with direction, which I'll call px. Yep. Wave vector has 3 Cartesian components, px, py, and pz. X component, and then the plane wave back again. And similarly for, if you just replace x with y, here and here, or you replace x with z. So 3 scalar equations. And I just want to focus on proving the first one. So let's do it. I need to write my plane wave out. So I've got e to the I into k dot r minus omega t. But let me write out k dot r explicitly as kxx plus kyy plus kzz. Now I could be a smart ass and change my coordinate system to get rid of everything but x, but let's not be that fancy. So minus I h cross d by dx acting on the plane wave. What thought pops into your head now? Besides how much you love quantum physics? Not a trick question. Minus I h cross. Any thoughts popping in? D by dx? Go for it. Same as before, absolutely. As far as d by dx is concerned, x is the only variable, so we're differentiating. So these constants come along for the ride. We're differentiating e to the I kxx via the chain rule, which just pulls out the coefficient of the x, which in this case is ikx. And everything else stays exactly as it is, and the everything else is the plane wave function, which I'll just write as follows to save chalk. Minus I squared, again, is 1. This h bar k, we remember the formula that the wave vector k is proportional to the momentum p of the plane wave. So this is nothing more than the x component of the momentum, which is precisely what we wanted to prove. Now, if I was to, and so we've proven this first equation. Now, I like elegance, so if I was to ask you this in an exam, not saying that I will or that I won't, don't write this out again for y and write it out for z. Just say similarly for y and z components, hence, and then write down the answer, right? So simplicity and elegance is good. I won't accuse you of cheating or being lazy if you do that. In fact, I welcome accurate but otherwise succinct and elegant answers. So we've just proven the two Schrodinger correspondence rules. The third exercise I want to look at is to investigate equation 15, that building of an arbitrary wave function as a sum of plane waves. So I take one plane wave, our understanding of which is now deepened. I multiply it by some coefficient that depends on the wave vector k that labels the plane wave. I make that coefficient infinitesimal. I put some pointless constant because of the particular convention I'm using for quantum physics. And then I add up that superposition of plane waves to make an arbitrary wave function. That's a Fourier integral, but it's also just a sum of plane waves. This is equation 15. And the question is to prove that this equation 15 obeys the Schrodinger equation. In particular, that it obeys a time-dependent Schrodinger equation. But the question says, show that this obeys the time-dependent Schrodinger equation in free space. And when I say in free space, that's synonymous with setting the potential V of RT to naught. So the time-dependent Schrodinger equation is minus h bar squared on 2m grad squared plus V, which is set to naught, all acts on psi, to give the energy given by I h cross d by dt. So we need to prove that this free space time-dependent Schrodinger equation is indeed obeyed by the sum of plane waves given in equation 15. Now you can do this problem two different ways. The more elegant way is to say, bugger this Fourier integral, this is a sum of plane waves, and the Schrodinger equation is linear. Since it's linear, it obeys the superposition principle. If one plane wave obeys the Schrodinger equation, and the Schrodinger equation is linear, then any arbitrary sum of plane waves, which is all 15 is, will also obey the Schrodinger equation. So let me repeat, the more elegant way is to say any one plane, or prove that one plane wave obeys the Schrodinger equation. You then observe that this is linear, hence an arbitrary superposition of plane waves, which is what this is, must also obey the Schrodinger equation. In fact, let's follow that logic, because it's more elegant, and I want to be elegant today. So all we need to do is to show that one plane wave obeys this equation. Now let me take the right-hand side and shove it on the... So let me take the left-hand side and shove it on the right-hand side. So I'll have I h cross d by dt, acts on the wave function. Plus h cross squared on 2m, grad squared, acting on the wave function, and that all gives naught. Now what's in round brackets is a linear differential operator. Yep. And we can give it a name. We could call it S. which is S for Schrodinger operator, because that's what it is. It's the operator in the Schrodinger equation. And this operator, script S, acts on the wave function to give naught. If we can show that the Schrodinger operator acting on a plane wave gives naught, we therefore know that, we also know that S is linear, then an arbitrary superposition of plane waves will also obey the Schrodinger equation. This is the elegant way to do it, which I'll do now. The ugly way, or the less elegant way to do it, which is what I've done in the notes, is just to apply this operator to this whole mess, bring the operator inside the integral, do all the differentiations, and what you'll pop out with is 0, as expected. But to be more elegant, let's prove that a plane wave obeys the Schrodinger equation. So let's do it. The Schrodinger operator acting on a plane wave. Now previously I unpacked the k dot r because I was a little bit confused and I wanted to write everything out explicitly, and I did it for the x and y and z components separately. Now that we've become more adept at such operations, let's not unpack the k dot r. Now we've seen this one before. I h cross d by dt acts on the plane wave to give the energy times the plane wave. That's what we did on the top right board. So we know that this first term already gives E. We have a h cross squared on 2m. Now you can do this component-wise again, grad dot grad, and then do it all component-wise, but let me do it the quick way with the chain rule. 1 grad, yep, so if you were to differentiate, right, e to the alpha times x, you'd pull out the alpha, right? If you were to take the gradient of alpha vector dotted with r vector, you just pull out alpha as a vector, right? Think about that, prove it to yourself with the chain rule. I'm going to use it now. 1 grad, which is differentiating essentially with respect to r, 1 grad will pull out an I times k. Grad dot grad, which is what grad squared is, will pull out ik dotted with ik. And then we get the plane wave back again, which I'll just write as follows. All right, what's next? Remember, we want this to be naught. Yep. The I and the I get together to give a negative sign. We've got h bar squared times the magnitude of k squared on 2m times the plane wave. But we know that P equals h bar k. And we also know that in free space that the energy of the particle is purely kinetic. It's half mv squared, which is the same as p squared on 2m. Hence, this difference is naught. Hence, this is naught. Hence, this is naught. So we've just shown that one plane wave obeys the Schrodinger equation. And since the Schrodinger equation is linear, an arbitrary superposition of plane waves also obeys the Schrodinger equation, QED. Thank you. As always, happy to answer questions after class for as long as you like.